Okay, going live here. We're live. All right, guys. So the first one I want to discuss, while I'm erasing here, you can think about it a bit. Look at 29. 29 is talking about so yesterday we did a problem involving a roller coaster where you're at the bottom of a circular loop. And so this problem is pretty similar. The amount of information you're given is a little bit different, I guess I should say the type of information you're given is a little bit different. And then also what you're solving for is different. You're solving for the speed. And you're also at the top of the loop. So it's different in, I'd say, 3 different ways. But ultimately, it's the same process. So hopefully this other example will make you all set for solving these. All right. So 29, we go, you're on a roller coaster, and you're going through a circular loop with a radius of 15 meters. Okay, so you're in a circular loop. You're at the top of the loop, so you're upside down right now. The radius is 15 meters. So let's start off with the simplest thing. What direction does the net force have to be pointing at this moment if you're traveling in a circular path? Towards the center of the circle. Okay. There's no way around that. That is a mathematical fact. Okay. Your acceleration and thus your net force must point towards the center. Okay. At this moment. Okay. Now I'm going to complicate things in a few minutes. Where if you're actually at a moment where you're speeding up or slowing down, so if you're like maybe at one of these positions, things get a little bit different, but we'll get to that in a second. But right now, you're kind of you're not speeding up or slowing down. So anyway, so what do? Well, we go F net equals ma. And now we need to talk about the force diagram. So what are the 2 forces exerted on you at this moment? Gravity. We draw that. Mg, right? That's always there. And then it says you feel half of your usual weight. So what's your usual weight?
140 pounds.
For you, that's mg. That's your mg value, right? But if you're in an accelerating object, if you're in a chair and that chair is accelerating in some way, well, what you feel is different, right? So you're accustomed to feeling mg. So maybe I'll draw it over here. Before you hit the loop, here's you in the car, and it's like mg cancels out. This is what you call your usual weight. It's a normal force, right? That's why you feel your weight. So right now, how much is that seat pushing on your bottom? Half of mg. Okay, so let's address any questions if there are any. Yeah, what are you accustomed to? You're accustomed to the chair pushing your butt with mg newtons of force. But at this moment in time, Colin, can you put that away, please? At this moment in time, since you feel half your usual weight, the seat is pushing you with 1/2 of mg. So, okay, what's the net force then, according to this diagram? Yeah, it's half of mg plus mg. They point in the same direction, so I add them up, right? Don't subtract them, that'd be crazy.
This is what we talked about yesterday.
And then if you're traveling in a circular path, you're at the top of the circle, your A value is V squared over R. Okay. Now, you might have noticed something about this problem. You might have gone, wait, it is impossible to figure out your mass for this question, right? But so I guess the question to be raised is, if Bob is 100 kilograms and Albert is 70 kilograms, do they both feel the same sensation at this moment? They're both on the roller coaster. Will they both be feeling the same weight reduction factor? And the answer would be yeah, because look at the physics here. What's going to drop out of this equation? Mass. So first, we maybe combine these. Half a banana plus a whole banana is 1.5 bananas. And then divide both sides by the mass. And it's an interesting result because certainly it's not obvious that a heavier man would have the same experience as a lighter man on this ride. But it's all ratios. So like, yeah, if you're a very heavy person, you'd feel half as heavy as usual. A very light person would also feel half as heavy as usual. It all comes down to just what's the speed and what's the radius of the loop. Notice this. The speed and the radius are both really important. So all we're going to do now is plug in the known values. So the radius is 15. And then we take a calculator.
Sorry.
Well, it's okay. So
Yeah.
1.5 times G. Right here. Maybe I'll write one more step. You have 1.5 times 9.8 equals v squared over 15. So multiply both sides by 15, and then take the square root. And if you do your calculation correctly, you should get a velocity of roughly 14.8 meters per second. So make sure that last step is something that's easy for you. All right, so what that tells you is that you can actually infer your speed in this situation based on how heavy you feel, which is kind of a weird fact if you think about it. Assuming you know the radius, so if say you can measure the loop, if you know how you feel inside the loop, then you can know how fast you were going. All right, let's look at 34. So all the other ones surrounding the two problems we went over involving roller coasters, I think should be sufficient for being able to look at every other problem and figuring it out. I guess I should show you this little demonstration here. Hopefully the ball's up there still. This little loop up here. It's not very groundbreaking or anything, but I guess for the fans at home, all I'm going to show is how if you roll this ball from here, it falls off the loop. It doesn't have enough speed to get around. There's going to eventually, when we start talking about energy, gravitational potential energy and kinetic energy, we can talk about how you can actually theoretically figure out what's the minimum height I can drop this from where it'll make it around. So like if I drop it from way up here, it's going to make it around. I think even something like this will be enough. Yeah, that was barely enough. So anyway, that's something we'll do later. But for now, all we're going to talk about is what's the minimum speed the ball has to have at the top of the loop in order to make it around. So
doesn't this have to be like kind of like sufficient where the speed is greater than like the gravitational and your net force pull down? Or
yeah, basically it's going to come down to well, the question we're going to answer is what's the minimum speed that you'd have to have at the top of a loop of a certain radius in order that gravity is what's providing the centripetal force to keep you in that circular path. That's the way we're going to kind of phrase it. So let's just answer it here. So 34, Stuntman Bob is going to drive his car around a circular loop of radius r. What is the minimum speed the car must have at the top of the loop in order to stay on the loop, not fall off? Okay. So Here's this car at the top of the loop. First, let's think about things in the simplest way. If he went around this loop super, super fast, would he feel heavy or light? Heavy, right? So if he went around the loop super fast, then the track would have to exert a lot of normal force downward, right, to keep him in that circular path. And he'd feel that normal force. He'd be like, wow, I feel very heavy right now. That's assuming he whips around the loop extremely, extremely fast. Okay? Aaron, you and I were talking about like in an airplane, right? If you're a pilot and you do a big loop, you do it pretty fast, you'd feel very heavy. You'd feel like I'm getting crushed, right? Same idea. It's the same principle. It's just that in this case, what's providing the centripetal force?
It's not the air.
Yeah.
It is? Okay.
Yeah, that's what provides the force to the wings. Yeah. Well, I guess who you're asking, because you ask the astronaut or whatever, the pilot, what's pushing on you? He says, the chair, the seat. What's pushing on the seat? Like the body of the plane, the metal, the frame of the plane. What pushes on the frame of the plane? The wings. What pushes on the wings? The air. What pushes on the air? The other air. That's what air pressure is. It's air pushing on air. So. Okay, so anyway, so this case, it's a little bit different. It's the track. The track pushes on the wheels push on the frame pushes on the chair pushes on its butt. Okay, so here's the difficult part, is imagining that if he was going at the minimum possible speed, obviously you can whip around this thing at 100 miles per hour and it'll work, right? But if he was going the minimum speed, how would he feel? He'd feel very light.
You feel like you would fall back to earth.
Right. He'd feel for a moment, he'd feel very light. So there's still this, that's called gravity, right? We all know about gravity. And the idea is that the normal force from the track would be approaching zero, or would be zero. Does that make sense? Okay, so the normal force can't push up unless he's in like a harness or something, or unless the wheels would have to be attached to the track in order for the track to pull up on the cart. But so if the normal force is zero, then who's providing all the necessary centripetal force to keep him in that circular path at this moment?
Wait, can you say that?
Okay, yeah. The question is, you guys get this one. Think about this one. What is providing? Right. So let me back up. In order to travel in a circular path, you need your net force has to be pointing towards the center, right? What is providing that force now? It's gravity. Yes. So a lot of times it's the track, right? So depending on where you are on the track, say at the bottom, well, gravity pulls down. The track pushes up very hard to keep you in that path. At the top of the loop, a lot of times, what usually happens is you have gravity and the track both pushing down on you. Sorry. The track is always pushing you, but if you minimize the speed, so if you reduce this normal force to zero, then that's the slowest you can do it. So anyway, I write the same formula, F net equals ma. Newton's second law. What's the net force if I carefully selected my velocity to make my normal force zero? What's the net force now? mg. And A is
E squared
over r. Now you see, wow, we're getting an extremely elegant relationship here. Okay, very simple. As happens a lot in physics, does the mass of the car matter? Nope. Or the driver, whatever. The mass drops out. R comes up here. And you get this very interesting relationship. Now, keep in mind, what kind of V is that? Is that his velocity?
That's velocity upside down.
It's his velocity at this moment, okay? So if he was the reason this gets complicated is, if he's in an actual car with an engine, then yeah, he can probably hit the speedometer and maintain that speed and make sure. but the car would tend to slow down as you went up the hill. So you'd have to actually hit the gas if you wanted to hit that speed. If you're doing your classic physics scenario and you're, like, say, rolling a ball towards the loop, you'd have to roll the ball faster than this so that by the time it got up to the top, it was going that speed. Does that make sense?
Yeah.
Okay, so that's a problem we'll do later. We'll answer the question, how fast does it have to be going here so that by the time it gets to the top, his velocity is at least as big as this, and he can make it around the loop. So, yes?
Can someone in theory run around the loop?
Yeah.
Without being attached to it?
Yeah, of course.
There's a video of it.
You can skateboard around a loop, I know that.
I didn't know if you like just physically run around it. It was like a super small loop.
It was tiny, but he like, it was going really quickly. Those
I imagine the difficulty would be, well, because as you can see from this formula, the bigger the R value, the bigger the loop, the bigger your velocity has to get. So humans certainly could not run around a loop if the radius was 50 meters, right? Because let's say R was 50, 9.8 times 50. You'd have to run 22 meters per second, which is not physically possible, I don't think. Is it?
Wasn't even Bolt.
What's Usain Bolt's top speed in meters? It might be 22.
It was like 9 or
11.
His average speed is roughly 10 meters per second, but his top speed might be like 6. Okay, his top speed was 12 meters per second, so not even close. So assuming you're Usain Bolt and you can hit 10, 11, 12 meters per second, that's under ideal circumstances. Anyway, so you need to pick a really small radius for it to work. But then the smaller the loop, the harder it is physically to hit. It's gonna be very steep when you hit that loop if it's a very small loop. So you guys found a video of it?
It's like pretty much like conducting a backflip.
It's got to be a small loop, right? On a skateboard, it's much easier because you can come off a ramp, gain a ton of speed. You can skateboard obviously a lot faster than you can run. So a lot of pro skateboarders and amateurs have done loops on a skateboard. Huh? That's a nice question. All right, one last thing. And this is, I'm going to show you this on the TV. Okay, look at number 35. So 35 might confuse you a little bit because it says, what's the net force vector on each diagram? Okay, so up to this point, I've been, in the interest of simplifying things, I've been saying like, oh, the net force points towards the center. The net force points towards the center. That's really only true if you're talking about either something moving at constant speed, say like the problems we did where it's like a ball attached to a string on a frictionless floor, so it's like in a horizontal rotational plane like this, then it's true. Or if it's at the bottom or the top of a loop, so say you're swinging something around, say the rotational plane is vertical, but it gets complicated if the thing is speeding up. Okay, so because here, let me point something out here. So like, you might go, well, we did problems involving like, a thing doing basically this, right? Well, at the bottom, it's actually hitting its maximum speed if you think about it. So it's actually changing from speeding up to slowing down. So for that little moment, it's basically traveling at a constant speed, which is a little confusing to think about, but if you think about it, it does make sense. Also in this scenario, just logically, there's only two force vectors. So the net force has to point up if it's doing this. If it's stationary, then the net force is 0. But Anyway, so what I'm trying to show you here is this. So what if we have a pendulum and I want to know where's the net force pointing as it's speeding up? So like, let's say when it's right here. Okay. Of course, it's like not even, okay, it's kind of showing up. I have to stay off screen. Okay. So watch this. So let me see if I point to it, it like, the thing goes white. That blue vector right there is what? Gravity. Okay. The red vector is the tension in the string. And then this dash, there's going to be two dashed blue lines. Those are just the components. Those are the radial and the tangential components of gravity, okay, with respect to this path. And then the purple vector is actually the net force. So watch what happens. It's really slow. So watch what happens as it moves. What do you see happening to the red vector? It's getting bigger. I can actually, maybe this is too slow. Let me try again. Just change it to like point. Triple the speed maybe? Let's try that. Okay, it's a little bit better. So as you can see, as it starts moving, that red vector has to increase. That red vector gets bigger, but what that means is that the net force vector is pointing kind of diagonally until it hits that point. Now what happened? Okay. Now the tension points left and up. Notice what's happening to the gravity. He never changes, but his two components are changing as it moves. Okay. So we come back now. Again, as it speeds up, the faster it goes, the more tension is required to keep it in that circular path. So as that vector grows, that net force vector changes a bit. Okay. How do you guys feel about that? Sense? Okay. So one more time. Here, I'll show you one more time. I'll just drag this. So this is a little bit faster. So pause there, for example. Well, the net force points sort of in between, like there's the tension points to the left and up, okay? So it's more up than the gravity vector is down, so you get a little bit of upward net force, and you also get a little bit of leftward net force. So anyway, last time. And there you go, there's real speed. And there you go. Okay, so to answer this question then, 35. So now that you've seen it, it's kind of trivially easy to write out the answer, right? So at the very beginning, he just got released. Okay, so if you don't have a computer simulation to help you, that's totally fine. You can reason it out logically. So what's his velocity when he's first released? Just as you release something, what's the velocity? 0. So if your velocity is 0, you don't really need, you don't really need you don't need a radial force, right? Because look at your formula. V squared over R, V is 0. So you've got your gravity, you got your tension. We've actually done this analysis before. It turns out that this is a bigger vector, sorry. I don't know, do you guys, does this ring a bell? How this component of gravity cancels out the tension and your net force just points you. Your net force is tangential. We calculated, I think this would have been a couple problem sets ago, but we calculated what's the initial acceleration of this system by looking at this vector. It ended up being, it ends up being related to like this angle here, if you might remember that. Theta ends up being, yes.
If the velocity is zero, the net force will be zero though.
No. Well, yeah, you don't want to mix up this and this. So, okay, so the net force isn't zero because you've got this gravity, right? And so he wants to go down. And so I can't, so the problem that I maybe is that's happening is I can't use this formula really because it's not traveling in a circular path yet, if that makes sense. And also this formula is only valid for traveling at constant speed. So if it's speeding up or slowing down, then talking about the net force becomes much more complicated beyond the scope of an intro physics of a class like this, like physics 101 basically. Does that make sense? I know it can be confusing to be like, that's why I put this problem on here because it's important to look at it, but it does confuse people because they're like, wait a second, this kind of like calls into question what we've been doing. So when you use this formula, it's really in pretty specific circumstances where basically the top or the bottom of the loop, or like I said before, if something's traveling at constant speed, like in a horizontal plane. So anyway, so let's move on here. So, okay, so right now the net force, maybe I should use blue or something. I'll do my net force in blue. When it's first released, the net force is tangential to the path. But, so as we can see, trust the computer. And I promise it's programmed correctly. I was very careful. Okay, so that purple net force points tangentially, and then, but now the velocity, right? Now there's some speed, right? Now that it has some speed, the tension is going to increase. Okay. Oh, I said I was going to make net force blue. Dang it. Sorry. Bad. Messed up. Just make your net force darker or something. Because again, you've got gravity, that didn't change, right? But now the tension's bigger. Big tension, right? So what that means, if you think about these vectors, is that this net force is no longer tangential. It kind of points, and it's not radial either. It kind of points somewhere in between. There's the net force. Okay. And again, that's because it's speeding up. Okay. So not only is the velocity positive, there's also acceleration happening. So that kind of complicates things. Now this is the simple one. 95% of the time when we do physics about circular motion, we're talking about this scenario, something being at the bottom or the top of a loop. So here it's much easier. You can say, okay, this is gravity. Obviously tension has to be bigger than the gravity vector, and so the net force points up, points radially. And then, of course, on the other side, it's just kind of a mirror image of this. So you've got gravity, you've got tension, and the net force points like that. Okay? So if I draw the little box, you add up two vectors. It's kind of like vector 1 plus vector 2 makes the net force vector. Okay. It's all right. I ended up talking longer than I thought it would take, but we still got 10 minutes to work on some problems. Monday, I'm going to cover the last little bit. I'm going to cover the banked turn problem, which is a little and then the airplane on the string, the famous conical pendulum problem. But and then we'll have some more work time on Monday and Tuesday. What's wrong, Kate? You okay? Okay.